In this video, I'll be walking through my notes on NCEA Level 3 Experimental Physics. A link to the PDF and a list of corrections is in the video description. What is uncertainty? No measurement can be perfectly exact. This is not just because of the limits of our technology. At a particle level, the universe is fundamentally fuzzy. For more details, look up Heisenberg's uncertainty principle, but in short, old physics would say that the electron is here, whereas new physics would say that the electron is everywhere, but mostly here. This is one of the foundations of quantum mechanics. To account for this, all measurements physicists make should also express the uncertainty of the measurement. For our purposes, the main sources of uncertainty are the limited accuracy of the equipment, human reaction time, and parallax error. Expressing uncertainty. The length of a stereo is measured. We can report this in several ways. We could report this as a range, saying that the stereo is between 32 and 38 centimeters. Another way of writing this is what we call absolute uncertainty, which would write this in the form of 35 plus or minus 3, where the plus or minus just means give or take. We could also express this as percentage uncertainty, where we could take our 35 centimeters, and then instead of writing the 3, we find what 3 is as a percentage of the 35, which is 9% to one significant figure, giving us 35 plus or minus 9%. As a general rule, all uncertainties must be rounded to one significant figure. Measuring uncertainty. There are two rules which we're going to use to determine the uncertainty of a measurement. Firstly, the half smallest division rule. Use this rule when the greatest source of uncertainty is from your equipment. The rule is that for any single measurement, the absolute uncertainty is half the smallest scale division. For example, an object is measured to be 320 millimeters. The smallest division on this ruler is 1 millimeter, meaning that these divisions here are 1 millimeter wide. The uncertainty is therefore half of this, which gives us 0.5 millimeters. The final measurement is therefore our zero measurement plus or minus 0.5 plus our end measurement of 320, once again plus or minus 0.5. Adding our green values gives us 320, and adding our uncertainties gives us 1 millimeter. Our second rule is the half range rule. Use this rule when the greatest source of uncertainty is not from your equipment. The rule states that for multiple measurements, the absolute uncertainty is half the range. For example, let's say that the period of a pendulum is recorded to be these values. Half the range is half the largest minus the smallest, which gives us 0.03 to one significant figure. Averaging all these numbers gives us 1.40, which as a rule, we round to the same decimal place as the uncertainty. So 0.03 is to 2 decimal places, so we round this to the same. Our final value is therefore 1.40 seconds, plus or minus 0.03 seconds. Calculating uncertainty. When values in a calculation have uncertainty, the uncertainty must also be calculated. When you are adding or subtracting a number, you add the absolute uncertainty. If you are multiplying or dividing a number, then you add the percentage uncertainty. For exponents, you multiply the percentage uncertainty by the power. So if we had 2.0 plus or minus 0.3, and we're raising that to a power of 3, that would equal 2 to the power of 3, which is 8, plus or minus 3 times 0.3, which is 0.9. Some quantities have zero uncertainty. For these, the above rules still apply. In other words, these rules will still work when the uncertainty is 0. And as a side note, recall that square roots are powers of a half. Graphs. In this section, we're going to brush up on the basic structure of a graph. We have the x-axis, and we have the y-axis. We have a linear gradient, meaning that it's a straight line without any curves. The intercept with the y-axis is what we call c, and when calculating the gradient m, that is our change in y, divided by our change in x. The equation of a linear graph is given in the form y equals mx plus c, where once again c is our intercept. When stating the equation of the line, you would substitute the values for m and c and leave x and y as variables. For example, y equals 2x plus 5. Nonlinear graphs. To analyze nonlinear data, we transform it onto a linear graph. Let's start with a square relationship. A square relationship has this curve here, where the slope gets steeper and steeper, and we can write it in the form of y equals mx squared plus c. To make this graph linear, instead of plotting x, we plot x squared. This works because although there is a square relationship between y and x, there is a linear relationship between y and x squared. This logic is the same for all of the examples that follow. For a square root relationship, we can write this in the form y equals m square root x plus c, where once again we have a square root relationship between y and x, but we have a linear relationship between y and the square root of x. An inverse relationship has this curve here, written in the form of y equals m1 over x plus c. To make this linear, we plot 1 over x instead of x. And for an inverse square relationship, which is similar to an inverse relationship but with a steeper decline, we plot 1 over x squared. Interpreting gradient. Consider an experiment that produces the following graphs. Here is our t against L, which we could identify as a square root relationship, meaning that we need to plot it against the square root of L, making it linear, and for example giving us a gradient of 10. If we know that the equation for this experiment is t equals 2 pi the square root of L over g, which is the equation for a simple pendulum, we can rearrange this in the form of y equals mx, which involves taking the L and putting it into its own square root. Where t is our y, 2 pi 1 over g is our m, and the square root of L is our x. We can therefore write our gradient as m equals 2 pi the square root of 1 over g, and solve this to determine g. So if we divide both sides by 2 pi, square both sides, and then take the inverse of both sides, we can substitute our m, which is 10, and get an answer of 0.39 meters per second. Nonlinear graph equation. Let's find the equation of the following graph. Staying with our square root relationship from before, plotting it so that it's linear. Let's say we identify our intercept as 3, and that we have a rise of 10 over a run of 5. Our gradient is rise over run, which is 10 over 5, which gives us 2, with units of seconds divided by the square root of a meter. And since our intercept is 3, we can write the final equation as t equals our gradient of 2 multiplied by our square root L plus our intercept of 3. Where this is our y, this is our m, this is our x, and this is our c. So we have our y equals mx plus c. Uncertainties in graphs. When values on a graph have uncertainty, we plot them as an area, not a point. The size of this area is indicated using error bars. So we have our graph here. In pink we see our error bars, which are indicating an area outlined with green. On our y-axis, this is 2.5 plus or minus 1.5, meaning that we've gone up and down by 1.5. And on our y-axis, this is 10, where we've gone backwards and forwards by 5. Essentially what this means is that our point could be anywhere within this area. If the error bars for a variable are too small to reasonably draw, they can be ignored. Just be sure to make a note justifying it. To find the gradient with uncertainty, we need to determine the lowest and highest possible gradient while keeping within the error bars. So if we have our graph here and our plotted points, the lowest gradient we can draw while staying between all of the bars is this blue line here, and the highest gradient is this orange line here. Note that although a lot of the time you can just draw a line from this point to this point and this point to this point, this is only allowed if the line still fits within all of the points. And so in this example here, I've shown a situation where it doesn't work, since if I drew my line a little bit higher, then it would go above the error bar here. The final value for the gradient is the average, which is the highest plus lowest divided by 2, plus or minus half the range, which is the highest minus the lowest divided by 2. Writing the report. In the remainder of these notes, I'm going to go through what might be required in the assessment. However, each school typically does things a little bit differently, and so the advice from your teacher will take priority over anything I say here. This assessment will involve conducting an experiment for which you'll write up a report, similar to last year, except now with a discussion of uncertainty. Your aim will typically be given. You'll need to state your variables. The independent is the variable you change to predetermined values. You must use at least 5. The dependent variable has a value that's dependent on the independent, and is the one that you're measuring. Your control variables are the variables that are kept constant to ensure a fair test. You should identify and explain how they will be controlled. Accuracy improving techniques could include repeating and averaging, measuring multiples at once, accounting for zero error, though note that digital doesn't count, for example stopwatches and tearing scales, and you may need to reduce parallax error. For your results, any graphed values should be recorded, all values should have their units identified, and all measurements should have a recorded uncertainty. For your graphs, the axes should be labelled with units, your scale should be appropriate to fit the data, any outliers should be eliminated with justification that you've stated, do not truncate the nonlinear graph, as doing so can disguise curves, and by truncate, I mean do that squiggly line thing, where instead of starting from 0, you can instead start from something like 10. This is fine for your linear graph, but not for your nonlinear graph. You must also make sure that you have accurate error bars. For your gradient, you need to find the highest and lowest gradient. Do not use the points, meaning that once you have done your graph, you have your plotted points, draw your trend line. You should find the gradient of this trend line without using the coordinates of your points. Your lines must fit all the points, except any outliers that you've identified, and you should calculate the gradient with your value of uncertainty. Your final calculation is to state the equation of your relationship, which you should write in terms of the actual values. So using L and T instead of X and Y. You should draw a comparison with theory, where you determine the theoretical gradient, does it agree with your experimental within uncertainty, and calculate the percentage difference. Your conclusion is a summary of your findings. For your discussion, explain any limitations of the theory, such as the small angle approximation, discuss how another variable could have affected the results, and discuss the potential causes of any unexpected outcomes. How to lose marks. In this section, I'm going to go through a list of things that will lose you marks or fail you outright. So to be clear, do not do the following. If you use less than 5 data points, that is an instant fail. 5 data points is specifically required by the standard, and so no matter how good the rest of your assessment is, your teacher will be unable to forgive this. Forgetting to state the units of a value could lose you marks, so you could write the units for each value in your results table, or to save time, just specify them in the top row. Truncating the graph can make curves hard to see. For example, if you had a trend like this, when truncated it will appear something like this, which in the worst case scenario might make you conclude an incorrect trend. Using points to find the gradient instead of the line will almost always lose you marks, so if you drew your change in y and change in x based on your points instead of based on your line. Forgetting to compare your experimental results with theory numerically could lose you precious excellence marks. For example, if you said the experimental value is close to the theoretical value, so my experiment was accurate, this is not specific enough to ever give you points for anything. Instead, you should say something like the experimental gradient of 32 newtons per meter is 6.7% higher than the theoretical value of 30 newtons per meter. If you express the equation in terms of x and y instead of the actual variables, this can prevent you from even getting a merit. Forcing your trend line through 0 is an absolute sin and is something that there is no reason to ever do. Do not play connect the dots instead of drawing a trend line, so don't do this. You should of course be doing this. Do not use imprecise language. For example, if surface area was not controlled, my results would be inaccurate, is too imprecise to mean anything. Instead say, if surface area increased, the object would fall slower, increasing the drop time. And finally, drawing a trend line outside the error bars is another good way of losing marks. In this section, we're going to be going through an exemplar. However, as stated before, every school might assess things a little bit differently, and so the advice from your teacher should take priority over anything I say here. For this exemplar, we're going to be doing an experiment on the simple pendulum. Our aim is to determine the relationship between the length and period of a simple pendulum. For our variables, our independent is the length, our dependent is the period. For our controls, we will control the angle of release. For this, a ruler will be positioned to ensure an angle of 10 degrees. We'll also control the mass of the bob. For this, a 0.2 kilogram mass will be used. For our accuracy improving techniques, the experiment will be repeated 3 times for each length, and the results will be averaged. The time for 10 swings will be recorded and divided by 10 to determine the period. For our results table, we have our lengths, our 3 trials of 10 swings, which I've then averaged and divided by 10 to find the period. The absolute length uncertainty is the smallest division, which is 0.001 meters. Our reaction time is estimated as 0.3 seconds. The reason I'm not using the half range rule is that the amount of data is so small that we can often underestimate our uncertainty. And so the absolute period uncertainty is the reaction time of 0.3 divided by our 10 swings, giving us 0.03 seconds. Plotting this on our graph, we see a square root relationship, meaning that we need to square root our x-axis value, which is our length. And now to find the uncertainty in our square root length, we need to take the absolute uncertainty in our length, find it as a percentage. Because a square root is a power of a half, to find our percentage uncertainty in the square root of L, we multiply the percentage uncertainty in L by a half. And then finally multiply this by our square root L values to find our absolute uncertainty in the square root of L, which is very small. We now need to do our period against square root L graph, making sure you have an appropriate scale to fit all of your data. Plot your points, draw the error bars. In this case, our length uncertainty is too small to draw. We now draw the lowest gradient we can while fitting within all of the error bars, and then the highest gradient, find a rise over run for each, and we'll also pick a point which we'll later use to find the intercept. Our theoretical intercept is 0, which we can see from our theoretical equation here, which should always be given to you on your task sheet. Now knowing that this is y and this is x, that means that this here is our m, our gradient, which knowing that the gravitational acceleration is 9.81 newtons per kilogram, and knowing the equation for our theoretical gradient is 2 pi the square root of 1 over g as mentioned above, we can substitute that value and find a theoretical gradient of 2.01. To calculate our maximum gradient, we use our change in y and change in x that we drew before, which gives us 2.4. Doing the same for our minimum gradient, our final gradient is the average of these two, plus or minus half the difference, which gives us 2.1 plus or minus 0.4. For our comparison, the experimental gradient 2.1 plus or minus 0.4 and theoretical gradient 2.01 differ by 4.2% and agree within uncertainty. We can find the intercept of our maximum gradient by knowing that y is mx plus c and that the gradient for our maximum gradient is 2.4. We can use the point that we drew on our graph before. Rearranging y equals mx plus c for c gives us c is equal to y minus mx, substituting in our point values, and also our gradient, gives us negative 0.22. We can do the same for our minimum intercept, and so our final intercept is the average of these two, plus or minus half the difference, which gives us negative 0.20 plus or minus 0.03. For our comparison, the experimental intercept of negative 0.20 plus or minus 0.03 and the theoretical intercept of 0 do not agree within uncertainty, a point that we'll discuss in our discussion. For our conclusion, the relationship between T and L is shown to be a square root relationship, in agreement with theory. The experimental and theoretical gradient differ by 4.2% and agree within uncertainty. For our discussion, the angle of release was kept to 10 degrees. As for angles above this, the small angle approximation becomes inaccurate for values expressed to 3 significant figures. This, meaning the small angle approximation, assumes the bob swings in a straight line and the weight component Fw sine theta is always horizontal. As a result, the experimental restoring force will be smaller than the theoretical, causing a smaller acceleration and overall velocity, and therefore a longer period. The theoretical intercept and experimental do not agree within uncertainty. This may be due to underestimating the uncertainty in length or time, or could reflect a systematic error. For example, the length is specifically the distance from the pivot to the center of mass. The center of the bob was approximated as the center of mass. This assumed the mass of the string was negligible. If this was untrue, all lengths would be longer, which would cause a negative intercept.